Let's touch on the governing equations again. We've already seen some form of it, but we will revisit them just to recap and remind ourselves. So this is the figure that is showing again how we typically use a grid system on a sphere. You have longitude, latitude, and often full spherical equations have to be solved when you do global coupled models. But when we do model equations and explain the models, and we want to learn the ocean atmosphere dynamics, for example, we always resort to doing Cartesian coordinates, which are local, of course, with x unit vectors in x, y, and z themselves moving because of the spherical geometry. So longitudinal direction is typically called x, latitude is called y, and the local vertical is called z. So you have x, y, and z with zonal velocity, meridional velocity, and vertical velocity. And you remember that vertical velocity is typically dealt with by, via the hydrostatic balance. So large scale circulation tends to remain in hydrostatic balance, but when you have very strong deep convection happening, you have obviously strong vertical motions which do not satisfy hydrostatic balance, but then the large scale quickly adjusts back to the hydrostatic balance. So those kinds of problems we dealt with. Looking at the F equal to ma in the Newton's second law for the zonal, meridional, and vertical directions, we wrote the total derivative, material derivative, Lagrangian derivative as du dt equal to the Coriolis term minus the pressure gradient term plus some frictional term. And similarly for the meridional direction. In the vertical, we almost always use the hydrostatic balance, even though there are models like the weather research and forecast model, which often tend to be run in non-hydrostatic mode as well. And of course you have the thermodynamic equation Cp dt dt minus 1 over rho dp dt equal to Q, which is typically the diabatic heating term which determines the circulation, so it becomes very critical. Of course you remember the other details, that in the atmosphere you have P equal to rho RT, so ideal gas law, which allows us to simplify many things, like using the pressure coordinate in the vertical rather than z coordinate, expressing vertical velocity in the pressure coordinate, which can eliminate the density term from the continuity equation and other equations. Ocean is typically very incompressible, so its thermodynamics tend to be simpler with Cw dt dt equal to Q. So we have for the air heat capacity at constant pressure, and dp dt is a strong term because it's a compressible fluid, whereas in the ocean pressure effects can be ignored, so you reduces to heat capacity of the water, and dt dt equal to Q. Divergence equal to minus del omega del z, where d is the defined in terms of the horizontal currents du dx plus dv dy. Actually this is dw dz, so then this becomes the ocean's continuity equation, because ocean seawater is incompressible, whereas for the atmosphere we can equate the divergence to d omega dp minus d omega dp, where we have basically used hydrostatic balance P equal to rho RT to eliminate rho and write W in terms of pressure velocity, so that's d omega, different than the W. So then divergence is minus d omega dp is the continuity equation for the atmosphere. And then you need a humidity equation in the atmosphere, which is very critical, similar to the salinity equation in the ocean. And the humidity does have a material derivative term like partial q partial t plus u dq dx plus w dq dy plus sorry, v dq dy plus w dq dz. But we also have parameterized convection, which supplies moisture to the free troposphere, and there is also mixing ratio, so there is a mixing term parameterized typically in the atmosphere because they are not resolved from the first principle equations or primitive equations. In the ocean you have a similar parameterized salinity budget where salinity mixing is included here. So that gives us a full set of equations, and of course we have to remind ourselves that the moisture dynamics is very, very, very important in the atmosphere, the most nonlinear part of the circulation very often. So values of water vapor content measured by vapor pressure versus temperature. The saturation vapor pressure as a function of temperature is given by this solid curve, which is what we called the Clausius-Clapeyron, which in a simpler form is written as dq dt, temperature dependence, as a times e to the minus beta t. So q is a times e to the minus e to the beta t, so exponentially increases with temperature. So if you are on this side in terms of the temperature range and the vapor pressure, then condensation, we say in India condensation, and in the US we say condensation. So here, to put one more molecule of water in, you have to drop out one molecule, so rain occurs with this kind of condensation. But here in this range of vapor pressure and temperature, relative humidity is lower than saturation, so 85% goes here, 65% relative humidity ends up being here. So if you want to saturate, you can either cool the water parcel or you can add water vapor and get here, right? If you go beyond that, you're going to have condensation. That also tells us about the moisture dynamics. So if you look at again temperatures versus pressure in the vertical, as we said, the z and p coordinates are used almost interchangeably. So when the water air parcel begins to rise, it may have moisture in it, unless you are on desert and moisture is basically negligible. Then the air parcel begins to rise along a dry adiabat, which is got lapse rate of almost minus 10 Kelvin per kilometer, whereas once it hits condensation level and water within the air parcel that is expanding and cooling because of the decreasing pressure, then the condensing water vapor releases the heat. So even though it may be rising adiabatically in the sense that it's moving so fast that it's not mixing with the environment, which is what we call the adiabatic rise. So then the lapse rate is lower because the heating due to the condensation makes the temperature drop much more slowly than the dry adiabat. So the moist adiabat tends to be much slower, but typically if you continue this line, the moist adiabat condenses at some point and the precipitation processes take out the water vapor, and in the upper atmosphere it comes back to the dry adiabat typically. Okay. So let me leave this podcast here and then come to the grids and parameterizations in the next chapter again. So this is again just continued introduction before we come to some aspects of climate change and how models are used for doing climate change simulations and projections. Okay.